This recording is one of a few early in the semester that serve two purposes. One of them is the sample calculation for the Unit 1 Density Lab, and the other one is for the Unit 1 lecture where I'm talking about significant figures, units, errors, qualitative, random versus systematic, the quantitative errors, computational. By the way, that will happen only here, that we talk about quantitative computational errors and outliers and median value. Okay, so anyway, just about get started. I'm going to use the data that I got in my sample density lab that I posted, do the calculations there, and I believe in this recording, as I posted on YouTube with a maximum of 10 minutes, I think I only have time for looking at significant figures, units, and just a little bit on errors. The actual error calculation and looking at the errors I'll do in another recording. Okay, let's get going. I used a sample, a cube of lead, and I looked up the density on the internet. It is posted as 11.35 grams per cubic centimeter. And now here's what I measured. 3.1 for the length, 3.1 for the width, 3.1 for the height, and 355 for the mass. And at this point I already got it wrong, and you would be marked wrong because any kind of measurement needs to take on a unit. So this is 355 grams. The height is 3.1 centimeters. And centimeters. In a video I said that I'm trying to measure this here as accurate to the closest half millimeter, so 0.05 centimeters, kind of in the divisions, in between the divisions of 3.1 to 3.2, kind of in the middle. So 0.05 centimeters. There we go, there we go. And then with the spring scale, I estimated that I was able to measure within plus minus 3 grams. And as I said, I will talk about the percentage error and how to calculate the error in a later recording. Okay, so at this point, let's figure out what the density is. The density is mass divided by volume. So I'm going to calculate the volume, which of course is length times width times height, and then I divide that into the mass. So let's get a calculator. 3.1 times 3.1 times 3.1 is 29.791. Of course, that could be a little bit faster if I did this. 3.1 cubed. There you go, same number. Now I divide this into 355. There we go. And I come up with 11.91 and so on. And on your lab sheet, it indeed says to write down the entire number from the calculator, so 11.91635058 grams per cubic centimeter. But of course, this is a total overkill. You're pretending that you measured this accurately. You did not. You measured 355, that's 3 significant figures. 3.1, 2 significant figures. 2 significant figures. 2 significant figures. And your result has to reflect that. The result cannot have more significant figures than the least of your measurements. And you have 2, 2, 2, and 3 significant figures, so your result can only have 2 significant figures. As I said, the least amount. So I'm going to look at 1 and 1. That is 2 significant figures, and now in order to round correctly, because of the 0.9 here, it comes out to 12 is the correct answer. 12 grams per cubic centimeter. Notice that that is actually relatively close to 11.35, and we can figure out later why it's not exactly 11.35, why it's around at 12. Okay, let's do the next example. I used an irregular shaped specimen, and it's galena, which is lead ore, lead sulfide, for which I looked up the density as 7.4 grams per cubic centimeter. But here are my measurements. I measured 50 grams, and then I immersed it in water and measured 45 grams, and the reason is that when I immerse it in water, water is pushing up on it with its buoyant force, and so it appears that its weight or mass has decreased. I believe the word or the expression apparent immersed mass, I even got that from our textbook. The calculation for this one here is different. Again, I wasn't able to determine the volume of the irregular shaped one because it's hard to measure, so I use this different way of doing it. By the way, the error here, I believe I said in the video 2 grams and 2 grams, and again I do the error calculation itself actually later. Then I'm going to calculate mass divided by the difference between the two masses. I could just about do that in my head because the difference is 5, and I would have to divide that into 50. But let me show you on the calculator. So it's 50 grams divided by the difference between the two, 50 minus 45. Make sure you put parentheses around that if you do that in one step, and of course it comes out to 10. And actually it just comes out to 10 because grams would cancel, but what happens here is what I just actually calculated is specific gravity being 10 as it compares it to water, and the density of water is 1 gram per cubic centimeter. That's why it works. The specific gravity of water is also 1, and that's why the two are equivalent. So as I write here just a 10 because the units would cancel, that's actually equivalent to 10 grams per cubic centimeter. That's because I immersed it in water. So 10, I look at significant figures, and how many do I write down? Well, I measured to two significant figures, the 50 and the 40, so just the 10. Now somebody could argue, well, I subtracted actually these two numbers, 50 minus 45, which is 5, so actually I only calculated one significant figure. But I have to write this 0 down here anyway as a placeholder. So I could figure, well, is it significant or not? Well, that is discussed in when I talk about zeros in other recordings. Okay, so I come up here with 10 grams per cubic centimeter, and when you compare that to the book or internet value, that's 7.4. So I'm somewhat off, but I think I mentioned it in a video that I had quite an inaccurate measurement as I was trying to take, for example, the 45 and saying, wow, plus minus 2, that's already quite a bit, especially once I subtract these two. Okay, because I wanted to talk about significant figures and units in this one and reserve errors for the next recording, I'm done for right now. So again, this is another recording that serves a dual purpose. One is to look at significant figures, units, errors, and so on, and the other one is a sample calculation for the lab on Unit 1 for density. So here I'm going to look at calculating errors. So these are the computational or quantitative errors, and then later on in this recording I'm looking at random versus systematic, respectively qualitative errors. So let's start with the computational ones. By the way, this is the only time ever you're going to do this. After that it will be just qualitative, that you're just going to say, well, this is what could have influenced my measurement, but you're not actually making calculations. So here's the only time that we ever do this. In order to, that is the computational errors, in order to determine the percentage error, I take my measurement error that I estimated at 0.05 centimeters and divide by 3.1 centimeters and shift the decimal point a couple of times, and that gives me the percentage error of that measurement. And then here I have 3 grams versus 350 grams. Again, I divide the two. That kind of looks like I've come up with a little bit less than 1%. So let me do the calculation. So first one is 3.1 divided by, no, not 3.1 divided by 0.05 divided by 3.1. So that's 1.6%. Remember, shift the decimal point. And that happens for length, width, and height in my case because I used a cube. And then it's 3 grams divided by 355 grams, and I come up with 0.8%. So that's what I have, 1.6%. Again and again, that's just because I have a cube. Notice that technically I should write the unit in behind, which is percent, but I already have written that on the top, and that's why I don't have to write it again. So those 4 errors, which I now add up at the percentage errors, so 1.6 plus 1.6 plus 1.6 plus 0.8 comes out to 5.6% of a total error. The 5.6%, I have to now look at what kind of error I have back here. So I have to take 5.6% of 12. Again, I'm going to look at, and again, I'm going to shift the decimal in order to actually calculate that. Okay, so here we go. 12 times 0.056. And that is 0.672. Because I multiplied my percentage as a decimal times the density of 12 grams per cubic centimeter, that is also why this one takes on the units of grams per cubic centimeter. And now, again, I have an overkill here of 0.672. I should round this to the ones place that I have here, the last significant figure, which is the ones place. So right here is where I should round it to, so I'm going to look at the next one that I have, the 6. So this one will round to pretty much just 1. And now look at my relatively large error, actually 1 gram per cubic centimeter. So it's 12 plus minus 1 gram per cubic centimeter, and look at the number that I had calculated in the previous recording that the calculator gave me, where I said, you know, this is a total overkill. And this number here, this computational error, justifies why I should get rid of all of this stuff here and then use this 1 digit here in order to round properly to 2 significant figures, which then 11.9 rounded comes out to 12 2 significant figures with an error attached of plus minus 1. Now, beyond that, I can also use my error of plus minus 1, and that gives me a kind of error range. So actually my measurement could be anywhere between 11 and 13. And now I compare it to the density that I found from the book or on the internet, and it says 11.35. And I say, well, because of my measurement error, I didn't come up with the exact number, 11.35, but I came up with 12. But my error is relatively large, 5.6%. respectively plus minus 1, that actually the book value falls within my measurement plus minus the error. So somewhere between 12 plus minus 1. So that error range actually allows me to say that my measurement is actually pretty good. I'm relatively close considering that I have a relatively large error of 5 or 6%. Let's look at the one with the irregular shape specimen. Here the calculation is somewhat different simply because we're not just dividing and multiplying, but at some point we're subtracting. And here, even though 2 grams compared to 50, it's only a 4% error, and 2 grams compared to 45, that's also about a 4% error. That's relatively small, but we're subtracting these two numbers, and that's 5 grams. And now that error of 2 grams is relatively large. Take, for example, had I not measured 45 but 46, and had I not measured 50 but 49, now I have a difference of 3, and now my error of 2 grams is pretty huge. I have, of course, 50 and 45, but still the difference is 5 grams, and compared to a 2 gram error, that's pretty large. So divide the error by the error of 2 grams in this case by the difference of 5 grams, so 2 divided by 5. 2 divided by 5, shift the decimal point by 2, and that comes actually up to 40%. I have a pretty huge error, 40%, and that comes from that the spring scale for small masses, in this case a small difference in mass, does become relatively inaccurate. So 40% error, which I now attach to the 10, and of course 10 times 0.4 is going to give me 4. We can type it in the calculator. 10 times 0.4 is 4 grams per cubic centimeter. And now I say that, well, I came up with, I have to shift, or maybe I have to zoom out a little bit. Hold on. Okay, that may work a little better, comparing the book density of 7.4 grams per cubic centimeter to the density that I calculate of 10 plus minus 4 grams per cubic centimeter because of that relatively large error. Again, I'm in the ballpark. I don't want to say that I came up with the exact number here. I didn't, because my error is relatively large. But also because my error is relatively large, I can say I'm in the ballpark. I'm, given my error, not too far off. And again, I will actually do yet another recording and talk about qualitative errors. Again, this is a recording that serves a dual purpose of looking at a sample calculation for Lab 1 on density, as well as for looking at certain aspects for a lecture such as significant figures, units, errors. So here I want to talk about qualitative errors, and I do it in the context of actually writing the conclusion for this particular lab. And here for the conclusion I would say, and of course it's mine, so don't copy it. For my conclusion I would say my result of 12 grams per cubic centimeter is relatively close to the accepted value of 11.35 grams per cubic centimeter. Within my error range that I computed. And the other one then would be minus what would be my result for lead, right? And then the other one would be my result of 10 grams per cubic for galena, which is lead ore, which is different. That's lead sulfide, it's a different compound. Is, well, somewhat close. I used the word ballpark, is in the ballpark when compared to the accepted value of 7.4. Still within my relatively large error range of 40%. So that or similar is what you would write. Now you also have to say what kinds of errors you encountered. So I always put a footnote on there that says the conclusion, of course, includes your assessment of the results, which is what I just did, and your error analysis, what could have caused random systematic errors, and be specific, mentioning friction without any specific errors. Simply mentioning an injudicious human error automatically leads to fewer points. So if I wrote down now that my measurements were influenced by human error, that automatically leads to me taking points off, because that absolutely has no meaning. What does that mean? Human error. I have no idea. You have to be specific in detail. By the way, as I'm typing here, of course I'm taking up time, but I want to show you that, well, you have to put a certain amount of thought into it, and that takes, of course, time. Okay, so here my measurements, perhaps I could express it as contain the following errors, and as I type here, and I'm speaking English in a second language, as I'm German. I may actually want to revise my sentence as it goes through here. I guess I'll see how this turns out. So my measurements contain the following errors. Measuring with the metric tape, with the measuring tape. So measuring tape, where I could have plus minus the 0.05 centimeters, so it's an estimated 0.1 centimeters or 0.05 centimeters within the divisions. Notice that the box does get larger, so you're not necessarily confined to the text box size that I gave you. It is the spring scale. The spring scale, that is, I express a little bit different. That's up to you how you express it. Accurate to within a few grams. And by the way, each one of these two here are actually random errors. Then I could say, well, what if I didn't tear my spring scale correctly? That means the original way of zeroing it, so the word would be to tear or zero the spring scale correctly, which is a systematic error. Let's say I had forgotten that, but since I shouldn't forget it, a systematic error is to be avoided. And the same for the measuring tape that I used. So tear or zero the measuring tape. I think I showed that in the video as well, that if I start at the wrong point, they're not at the zero, but at the end of the measuring tape, that is not the same. I think I used a ruler actually. So measuring tape or ruler and spring scale, I get a systematic error that I should avoid. Now, in my case, you may have seen it as I hooked on the lead cube. You may or may not have noticed that there was a little hook on the top, which is actually a brass hook. So my lead cube actually contained a brass hook that should not be measured, but I tried to take it off beforehand and I couldn't, and besides it was actually convenient to hook it onto the spring scale. So my lead cube actually contained a brass hook that should not have been measured, but it did, and again that would be a systematic error, which in this case I couldn't avoid. Then I definitely saw that my lead cube, actually lead is relatively soft, was actually chipped. So lead cube was chipped, and because of that, the volume that I measured was perhaps a little bit too large than what it should have been. And in this case, I really couldn't avoid that, but I have to note it down. And that is what I would expect in a conclusion. I believe I'm done here with my qualitative errors. There isn't much more that I could do wrong on trying to measure the dimensions and the mass of a specimen. So that's how it would look like. You come up with comparing your results, and then you come up with an error analysis. And usually, as I said, that's going to be qualitative, just the way I wrote it here. And only for this particular lab did you have a computational error.